Linear Algebra II, Lecture 15, Quadratic Forms. Let V be a vector space of dimension n. A map Q from V to real numbers is called a quadratic form if there is a basis bold V in V and an n times n matrix Q with real coefficients such that the value of our map bold Q at any vector x in V can be computed as the product of the coordinates of x in the basis bold V transposed times our matrix capital Q times the coordinates of x in the basis V. For example, the zero map is clearly a quadratic form because for any basis bold V, we can take capital Q to be the zero matrix, and then Q of x will be 0 for any x in V. So the zero map is a quadratic form. Example 2, if E is an Euclidean space, then the map bold Q, whose value on an element x in V is equal to the inner product of x with itself, is a quadratic form. Indeed, if we take any orthonormal basis V, then we can take the matrix Q simply to be the identity matrix, because the scalar product of x with itself in an orthonormal basis is given by taking the coordinates of x with respect to this basis transposed times the coordinates of x. A vague intuition, so if we have a vector space V and we equip it with a quadratic form, this defines on V some sort of geometry if we interpret Q of x as a square of the length of x. So this is motivated by the second example. However, this geometry might be very different from the familiar to us Euclidean geometry because we do not require from a quadratic form to be positive definite. The quadratic form in example 2 is positive definite, so it takes positive real values on non-zero vectors. In the general definition of a quadratic form, this is not required. Let us first discuss how the expression for the quadratic form changes if we change a basis. So let bold Q be a quadratic form on V. Let bold V be a basis of V, such that the value of our form bold Q at x is computed as in the definition. The coordinates of x in bold V transposed times some matrix capital Q, it's an n times n matrix with real coefficients, times the coordinates of x in the basis V. Let now W be another basis in our vector space, and let T from V to W be the transformation matrix between these two bases. Then we know the base change formula for coordinates. The coordinates of any vector x in the basis V can be computed as the transformation matrix T times the coordinates of the same vector x in the basis W. So now if we plug in this into the formula for our quadratic form, we get that bold Q of x is equal to the transpose of T times x's coordinates in W times Q times T times x's coordinate in W. And we can rewrite this as follows. So Q of x is equal to the coordinates of x in W transposed, then times the following matrix, T transposed QT, and then times the coordinates of x in W. Consequently, for any basis W, we can find an n times n matrix Q prime with real coefficients such that our quadratic form Q, evaluated at any vector x in V, can be computed as the coordinates of x transposed times this matrix Q prime times x. So for any basis, we can find such matrix. However, this matrix is not uniquely defined. So let us now discuss non-uniqueness of this matrix. So let Q be a quadratic form on V. So let bold V be a basis in V such that the value of our quadratic form at any vector x is computed as the coordinates of x in V transposed times some matrix capital Q times the coordinates of x in V. And now assume that we have another matrix Q prime which gives us exactly the same value. So Q of x is now equal x's coordinates in V transposed times Q prime times x's coordinates in V. The claim: this is possible if and only if, for all I and j, the following equality holds. If we take the ij's element in the matrix Q and add to the ji's element in the matrix Q, the sum is equal to the sum of the ij's element in the matrix Q prime plus ji's element in the matrix Q prime. So the matrices Q and Q prime define the same quadratic form if and only if this equality holds for any I and j. Proof. Assume first that this equality holds for any I and j. Then the value of Q at the vector x can be computed as the product of x's coordinates in V transposed times the matrix Q times x's coordinates in V. So if we spell this out, we get a sum over all I and j, qij times xi times xj. So here we can take out the diagonal part. So this is a sum over all I, qii times xi squared. And in the rest, we know that xi xj is equal to xj xi. So we can write the rest of the sum as a sum over all I which are smaller than j. And then the coefficient would be qij plus qji times xi xj. And we can, of course, write a similar expression for the matrix Q prime. So if we take the coordinates of x transposed times Q prime times the coordinates of x, this is a sum over all I and j of qij primed xi xj. We take out the diagonal part, so this is a sum over all I, qii primed xi squared, plus the sum over all I smaller than j, qij primed plus qji primed times xi xj. And by our assumption, the coefficient here, qij plus qji, is equal to the coefficient here, qij primed plus qji primed. And also, by the same assumption for I is equal to j, qii is equal to qii primed. So this sum, the magenta sum here, is equal to the violet sum here. In other words, the expression with Q prime also determines the value of Q at the vector x. So this proves our proposition in one direction. So now let us prove the proposition in the other direction. So assume now that the matrices Q and Q prime are such that the corresponding expressions for Q and Q prime give us the same value for any x. So this means exactly, if we spell out both the left-hand side and the right-hand side, that the sum over all ij of qij xi xj is equal to the sum over all ij of qij primed xi xj. So now let us take x to be vi, so one of the basis vectors. Then the coordinates of this vector in our basis are, all of them are 0 except the coordinate number I, which is 1. So the xs, the element xs here, would be equal to 0 if s is not equal to I, and it would be equal to 1 if s is equal to I. And then the left-hand side gives us qii, and the right-hand side gives us qii primed. So the diagonals of both matrices coincide. Next, consider the vector vi plus vj. then all coordinates are 0, except for the coordinates I and j, which are equal to 1. And now if we plug in here a vector where all coordinates are 0 except for 2 which are 1, we will get the expression qii plus qjj plus qij plus qji is equal to qii prime plus qjj prime plus qij prime plus qji prime. Note that we already proved that qii is equal to qii prime, so we can take this away, and qjj is equal to qjj prime. We can take this away as well. And then we will get qij plus qji is equal to qij primed plus qji primed. And this completes the proof of the proposition. Now we can talk about the matrix of a quadratic form. So let Q be a quadratic form on V, and let bold V be a basis in V. Claim, if we consider all matrices, all n times n matrices with real coefficients, for which we can express the value of Q at x such that this is given by x's coordinates in V transposed times the matrix Q times x's coordinates in V for any x in V. If you consider the set of all these matrices, this set contains a unique symmetric matrix. So this is a matrix in which the ij's entry is given by qij plus qji divided by 2. Definition: this unique symmetric matrix Q, which has the property that the value of our quadratic form at any vector x is given by this expression for the matrix Q for all x in V. So this symmetric matrix Q is called the matrix of the quadratic form bold Q in the basis V, and denoted as we usually denote matrices, the matrix of Q in the basis V. From the previous slide, we already know how the matrix changes if we change the basis. If we take another basis, W, with the corresponding transformation matrix TVW, then the matrix of Q in the basis W is equal to the transposed of the transformation matrix times the matrix of Q in V times the transformation matrix. And we can note that this expression automatically gives us a symmetric matrix because, so if we take the transpose of this, we should write the transposes of each factor, but in the reverse order. So the transpose of the transformation matrix and the transformation matrix simply swap places, and when you take transpose, nothing happens, and the middle part is, by assumption, symmetric. So this is the base change formula for quadratic forms. Here is an example. Consider the vector space R2 with a standard basis E, E1, E2. For a vector x with coordinates x1, x2, consider the quadratic form Q, which evaluated at this x is equal to x1 squared plus 2x1, x2 plus 4x2, x1 plus 6x2 squared. Then we can write this expression as the row x1, x2 times the matrix 1, 2, 4, 6 times the column x1, x2. But we can write the same expression as the x coordinates times the matrix 1, 1, 5, 6 times the x coordinates as a column. This is because 2 plus 4 is equal to 1 plus 5. Yet another matrix, we can write the same quadratic form as the coordinates transposed times 1, 6, 0, 6 times the coordinates. This is because 0 plus 6 is equal to 1 plus 5, and it is equal to 2 plus 4. And the only symmetric matrix for which we can write a similar expression would be the matrix 1, 3, 3, 6. So this symmetric matrix is the matrix of our quadratic form Q in the standard basis. Let us now discuss quadratic forms in Euclidean spaces. Let E be an Euclidean space of dimension n. and let bold Q be a quadratic form on this Euclidean space. Theorem: there exists an orthonormal basis bold E in our Euclidean space E, and real numbers lambda 1 and so on lambda n, such that for any x in the Euclidean space E, the value of our quadratic form at x is given by the formula, the sum over I from 1 to n, lambda I xi squared, where x1, x2, and so on xn are the coordinates of x in the orthonormal basis E. In other words, this says that the matrix of our quadratic form bold Q in this orthonormal basis E is the diagonal matrix with lambda 1, lambda 2, and so on lambda n on the main diagonal. Proof: the matrix of Q in any orthonormal basis V is symmetric by definition. If we consider the linear operator given by this symmetric matrix, we know that such linear operator is diagonalizable in some orthonormal basis E. Further, recall that the transformation matrix between two orthonormal bases is orthogonal. And therefore, the base change formula for linear operators between orthonormal bases is the same as the base change formula for quadratic forms. So for quadratic forms, the base change formula is the transformation matrix transposed times the original matrix times the transformation matrix. For linear operators, the base change formula is the transformation matrix inverse times the original matrix times the transformation matrix. But orthogonal transformation matrices are exactly those matrices for which the inverse coincides with the transposed. And this gives us this property. Therefore, the matrix of Q in our orthonormal basis E, which diagonalizes our linear operator, coincides with the diagonal matrix for the linear operator with some lambda 1 and so on lambda n real numbers on the main diagonal. And this implies our statement. Here is an example. Let us solve the following problem. Let us diagonalize in some orthonormal basis the quadratic form on E2, which is given by the expression q of x is equal to x1 squared minus 4x1 x2 plus x2 squared in the standard basis. Note that the standard basis is an orthonormal basis in E2. Solution. So the matrix of this quadratic form is the matrix 1, minus 2, minus 2, 1. So the coefficients on the diagonal are just coefficients at the squares, and the coefficients of the diagonal are 1/2 of the corresponding coefficients. So we have x1, x2. This corresponds to the position 1, 2. Here we have the coefficient minus 4. We should write 1/2 of it in the position 1, 2, and 1/2 of it is in the position 2, 1. So we have this symmetric matrix, and we need to diagonalize it in some orthonormal basis. Let us do this. We start by computing the characteristic polynomial of this matrix. So we subtract minus lambda at the main diagonal, and we need to compute the determinant of the matrix 1 minus lambda minus 2, 1 minus lambda. So this is equal to 1 minus lambda squared minus 4. This is a difference between two squares, so this is 1 minus lambda minus 2 times 1 minus lambda plus 2, which gives us minus 1 minus lambda times 3 minus lambda. So we have two eigenvalues, minus 1 and 3, both with algebraic multiplicity 1. To determine the eigenvectors for the eigenvalue minus 1, we need to solve the homogeneous system of linear equations whose matrix is obtained from the matrix of our quadratic form when we subtract minus 1, in other words, we add 1, on the main diagonal. So we have the matrix 2 minus 2 minus 2, 2. So clearly we can erase the second row, and then it is very easy to guess that the vector 1, 1 is a solution to this system of linear equations. So since the algebraic multiplicity is 1, the geometric multiplicity must be 1. So this vector, the vector v1, which is 1, 1, forms a basis in the eigenspace for Q with eigenvalue -1. Similarly, let us determine the eigenvectors for the eigenvalue 3. So these are the solutions to the homogeneous system of linear equations with the matrix, the original matrix, -3 on the main diagonal. So we get the matrix -2, -2, -2, -2. And here it is also easy to guess that the vector v2, which is equal to 1, -1, forms a basis in the space of solutions. And hence this vector is a basis in the vector space of all eigenvectors for Q with eigenvalue 3. So the vectors v1 and v2, they are automatically orthogonal because they are eigenvectors for a symmetric linear operator corresponding to different eigenvalues. So to get an O and B, we only need to norm these two vectors. The length in both cases is the root of 2. So if we norm them, the W1 becomes V1 divided by the norm, which is 1 divided by the root of 2 times 1, 1. And W2 is V2 divided by the length of V2, which is 1 divided by the root of 2, 1, -1. So the diagonal form of our symmetric linear operator is the matrix -1, 0, 0, 3. So this is a diagonal matrix with our eigenvalues on the main diagonal. And the transformation matrix is 1 divided by the root of 2, 1, 1, 1, -1. So the expression for our quadratic form in this orthonormal basis will be minus y1 squared, this is this term, plus 3 times y2 squared, where y, which is equal to y1 and y2, so these are the coordinates of the vector y in the basis w1, w2. Let us also talk about the signature of a quadratic form. Let V be a vector space of dimension n. Let Q be a quadratic form on V. Let bold V be a basis in V such that the matrix of the quadratic form in this basis is the diagonal matrix with lambda 1 and so on lambda n on the main diagonal. Definition: the signature of our quadratic form Q is the pair a comma b of two non-negative integers, where a is the number of indices between 1 and n, for which the corresponding lambda I is strictly positive, and b is a number of indices between 1 and n, for which the corresponding lambda I is strictly negative. For example, on the previous slide, we had a quadratic form whose matrix in the basis where it is diagonal was -1, 0, 0, 3. So here we have one positive diagonal element and one negative diagonal element. So this particular quadratic form has signature 1, 1. One positive element and one negative element. Please note that to define this signature, we have chosen a basis V. So to be very precise, one should say this is the signature of Q with respect to the basis V. However, on the next slide, we will see that indeed the signature does not depend on the choice of the basis, and this is a statement which is known as Sylvester's law of inertia. Theorem: Sylvester's law of inertia. The signature of Q does not depend on the choice of the basis V. And because of that, we can introduce the notation, so the signature of Q is defined as the pair A, comma, B. Proof. We will say that the quadratic form Q is positive definite on a subspace W of V, provided that the value of Q at any vector x of the subspace different from 0 is strictly positive. And we claim that the first number A in the signature of Q coincides with the maximum dimension of a subspace of V on which Q is positive definite. This property, of course, doesn't depend on the choice of the basis, and this will give us independence of A of the choice of V. So first, let us assume that the matrix of Q is diagonal for some basis V. Assume further that exactly lambda 1 and so on lambda A are positive and all other lambda i's are not positive. So we organize our diagonal matrix so that it starts from the positive eigenvalues. Let W be the linear span of V1 and so on, VA. So these are exactly the eigenvectors for these positive eigenvalues. Then, if we take any linear combination of V1 and so on, VA, the value of our quadratic form at this linear combination will be the sum I from 1 to a lambda I xi squared. Since all lambda I are positive, this is non-negative. Moreover, it is 0 if and only if x is 0. Therefore, W is a subspace of dimension A on which Q is positive definite. So if we have A positive eigenvalues, we have a subspace of dimension A on which our quadratic form is positive definite. Let us denote by U the linear span of all Vi for I strictly greater than A. Assume now that W prime is a subspace of V on which Q is positive definite. Then the claim is that W prime and U intersect at 0. And this is true because the evaluation of Q at any element x of U is given by the sum I from a plus 1 to n lambda I times xi squared. Since all lambda i's for I greater than a are either 0 or negative, this expression gives us a non-positive real number. And by assumption, the restriction of Q to W prime should be positive definite. So this implies that the intersection of W prime and U is 0. But this means that the dimension of W prime is at most the dimension of V minus the dimension of U, which is equal to the dimension of W. This shows, indeed, that our number A can be interpreted as the maximal dimension of a subspace, the restriction of Q to which is positive definite. Similarly, by looking at subspaces on which Q is negative definite, we show that B doesn't depend on the choice of the basis. And this completes the proof of Sylvester's law of inertia. Let us solve one more problem. Problem: determine the signature of the quadratic form on R3, which is given by the following formula in the standard basis. So the formula is Q of x is equal to x1 squared plus 2x2 squared minus x3 squared plus 2x1 x2 minus 2x1 x3 plus 4x2 x3. Solution: the easiest and fastest way to solve such a problem is to rearrange the expression for the quadratic form by completing the square. So let us look at all summands of our expression which contain x1. So this is x1 squared plus 2x1 x2 minus 2x1 x3. So we can write this as x1 plus 1/2 of this coefficient, which is 1, plus x2 plus 1/2 of this coefficient, which is minus 1, minus x3 squared. And then when we open this square, there will be additional summands, x2 squared, so we subtracted, x3 squared, so we subtracted, and minus 2 x2 x3, so we subtracted, so we get plus 2 x2 x3. So now the teal part here is equal to the teal part of this expression. And then we copy the rest, plus 2x2 squared minus x3 squared plus 4x2 x3. So we simplify this expression to x1 plus x2 minus x3 squared plus 1x2 minus 2x3 and then plus 6x2 x3. Now we look at all terms which contain x2 squared plus 6x2 x3. So we call x1 plus x2 minus x3 by y1. So this gives us y1 squared. And then we have x2 plus 3x3 squared. So when we take the square, there will be an additional 9x3 squared, which we should subtract. And then we have minus 2x3 squared, which we just copy. So we have y1 squared plus, we call x2 plus 3x3 y2 squared, and then minus 11x3 squared. So we have now an expression of our quadratic form, which is just a sum of squares with some coefficients. So the signature of our form is 2, 1, because we have two positive coefficients, one here and one here, and one negative coefficient here. So this quadratic form has signature 2, 1. Here's another example. Let's solve the following problem. Find some basis in R3 which diagonalizes the following quadratic form. Q of x, which is equal to x1, x2, plus 2x1, x3, plus 4x2, x3. Again, if we just need to diagonalize the form, the easiest way is to complete the square. The problem is that there are no squares here in the formula, so we need to start by creating some squares via the so-called hyperbolic choice of bases. We look at new coordinates, y1, y2, y3, such that x1 is y1 plus y2, and x2 is y1 minus y2, and x3 is equal to y3. With these new coordinates, we have the following expression for q. From here, we get y1 squared minus y2 squared, so this is x1, x2. Then from the second summand, we have 2y1, y3 plus 2y2, y3. And from the last summand, we have 4y1, y3 minus 4y2, y3. So this simplifies to y1 squared minus y2 squared plus 6y1, y3 minus 2y2, y3. Now we can complete the square. So the summands which contain y1 are y1 squared and 6y1, y3. So we have y1 plus 3y3 squared. This gives us extra 9y3 squared, which should be subtracted, and then we copy the rest. Now here in this expression, we have y2 squared and minus 2y2, y3, which contain y2. So we also denote by z1, y1 plus 3y3. So we have z1 squared minus y2 plus y3 squared, because we had minuses here, so minus y2, and then in the brackets would be plus y3 squared. So this gives us an extra minus y3 squared, which should be compensated for. And then we copy minus 9y3 squared from this expression. The outcome is this expression, and now we call y2 plus y3 z2. So we have z1 squared minus z2 squared, and y3 z3 minus 8 z3 squared. So the second base change is given by the formula that the coordinate z1 is y1 plus 3y3, z2 is y2 plus y3, and z3 is y3. So we can rewrite it as a base change in the opposite direction. So from the last equation, y3 is just z3. Now from the second equation, y2 is z2 minus y3, which is z2 minus z3. And from the first equation, y1 is z1 minus 3y3, which is z1 minus 3z3. So we have two base changes. The x coordinates can be written using y coordinates in this way, and y coordinates can be written using z coordinates in this way. So x1 is y1 plus y2, x2 is y1 minus y2, and x3 is y3. y1 is z1 minus 3z3, y2 is z2 minus z3, and y3 is z3. So if we combine them, we get the expression that x1 is z1 plus z2 minus 4z3, and x2 is z1 minus z2 minus 2z3, and x3 is z3. So this means that the transformation matrix from the basis where you have x coordinates to the basis where you have z coordinates is the corresponding coefficient matrix, which we read by rows. 1, 1, minus 4, this is from here, 1 minus 1 minus 2, from here 0, 0, 1. And this completes the solution of our problem. So in the basis given by this transformation matrix, here is the expression for our quadratic form. So in particular, it has signature 1, 2, 1 positive coefficient and 2 negative coefficients. Remark, it is very tempting to use the technique of diagonalization in an orthonormal basis when working with a quadratic form. However, in general, this is much more complicated problem than diagonalization using completion of the square. And this is because in order to diagonalize it in an orthonormal basis, we need to compute the roots of the characteristic polynomial of some matrix. For small matrices, this is easy, but for big matrices, this is actually not really possible. Therefore, diagonalization using completion of the square is much faster and much more handy. Let us finish with some problems and questions. Question 1. Let Q be a quadratic form on V. Check that for any vector x in V and any lambda a real number, the value of Q at the vector lambda x is equal to lambda squared times the value of Q at x. This is a justification for the term the quadratic form. If you want to take away a scalar, you should take it in the quadratic version. Question 2. Let P and Q be two quadratic forms on V. Is the sum P plus Q also a quadratic form? Question 3. Diagonalize in sum O and B the quadratic form Q of x given in the standard basis of E3 by the expression x1 squared plus x2 squared plus x3 squared minus 2x1 x2 minus 2x1 x3 minus 2x2 x3. Question 4. Determine the signature of the quadratic form on R3, which is given by the following formula in the standard basis. Q of x is x1 squared minus x2 squared plus 2x3 squared minus 2x1 x2 plus 2x1 x3 plus 6x2 x3. And finally, question 5. Let P and Q be two quadratic forms on V such that P is positive definite. Prove that there is a basis bold V in V which diagonalizes both P and Q simultaneously. Thank you very much and see you next time.